Before we get into talking about functional groups and different types of molecules, we want to spend a little bit of time talking about how we represent the structures of molecules from different methods we have called condensed formulas and line drawings. So one of the issues that comes with the variety and flexibility of organic molecules is the problem of structural isomers. So these are molecules that have the exact same chemical formula, but different bonding patterns. So for example, C2H6O, molecules containing 2 carbons, 6 hydrogens, and 1 oxygen, you can either have ethanol or you can have dimethyl ether. These have the exact same chemical formula because they have the exact same numbers of atoms, numbers and types of atoms, but they're arranged differently. Namely, you can see it's carbon bonded to oxygen, or carbon bonded to oxygen, bonded to carbon. So it's the carbon oxygen in the middle or on the side of the 2 carbon atoms. And this leads to very different properties. So for example, dimethyl ether boils way below room temperature, so it's a gas at room temperature, whereas ethanol is a liquid at room temperature. It's a liquid well above room temperature. So that's just the physical properties are very different. Also, just the chemical properties are different. These do different things. They have different sorts of reactivity. And so just showing the chemical formula will not be enough when we talk about organic molecules. We will need to describe the structure of a molecule whenever we're talking about it. These issues with isomers and isomerization grows exponentially as you have a larger and larger molecule. So C5H12, for example, has 3 different isomers. C10H22 has 75. So just as you add slightly, a couple more atoms, there's a lot of possible types of bondings. Are all the carbons just boom, 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 boom in a row? Or does it kind of branch out? Or does it really branch out in the case over here? So you have these sorts of, carbon's just going to form 4 bonds, but are they all bonds to other? How many bonds to carbon? How many bonds to hydrogen? There's a lot of flexibility, and it comes from one of the things that's really unique about organic molecules is, again, the fact that carbon is forming bonds with other carbon atoms, and that really opens up the possibilities for forming different isomers in lots of different shapes. Participation 428, question 1. Are the following molecules isomers? Explain your answer. This is the first question on participation 428, due Tuesday, April 28th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, are the following molecules isomers? One molecule and 2 molecules. I got 2 of them and I want to know, are they isomers? You want to explain your answer. So a lot of times we use what are called condensed formulas to describe organic molecules. And what this is, it's like a molecular or chemical formula where it's just, the atoms, but there's a little bit of structural information. We write the atoms in the order of bonding, and we're really just looking at kind of the non-hydrogen atoms. Our hydrogen atoms are just kind of be looked at as decoration, like we've seen previously when we're making Lewis structures. And so we really are looking at what is the kind of connections between the non-hydrogen atoms. So for example, pentane, we have our condensed formula where all the carbon and hydrogens are written out, and then we can also, that's conveying the shape of the Lewis structure, the actual kind of organization. So we have the first carbon atom, the second carbon atom, third, fourth, and fifth. And the hydrogens are just written next to or right after the carbon atom that they're bonded to. So this carbon atom is bonded to 2 hydrogens, and they are just right there, kind of hanging off to the side. So those hydrogens are basically following what non-hydrogen atom they are attached to. If we look at ethanol, this was one of the isomers we wanted to convey, right? So we have the first carbon atom, second carbon atom, and then the oxygen's third, whereas in dimethyl ether, it was carbon, oxygen, carbon. So we write those in that order to convey. And you'll note for the oxygen, the middle oxygen, dimethyl ether, it's not bonded to any hydrogen atoms, consistent with this representation where it's just O in the condensed formula. We can start to represent more complicated bonding patterns in condensed formulas by using literal branching. So for example, isobutane, the carbon atoms don't all bond in a row. Instead, there's kind of this row right here and then something sticking out the top. So this is sticking out the top. In propene, there is a double bond between two of the carbon atoms, and you literally can write the double bond in the condensed formula. Should be noted, you don't actually have to. You could figure out, based on the fact of how many hydrogens are bonded to these carbon atoms, that there has to be a double bond there in order to fill octets. But you can also convey that in condensed formulas. Acetylene has a triple bond. So that triple bond right there shows up right here. When we're looking at condensed formulas, we do want to be careful that sometimes when we write out condensed formulas, there is some variability in writing them that makes it look like you're talking about two different shapes of molecules, therefore two different isomers, but not quite. So this top example, C6H14 on the left, you have all 6 carbon atoms written in a row, one bonded after the other. The representation on the right, we have the 3 right there, and then it kind of looks like you're conveying some sort of branching, but really that's just 4, 5, 6. That's the exact same molecule. It's just written in a different way. And this is getting at one of the important ideas of we are representing the connectivity of molecules, not necessarily the perfect shape. We're just saying this is how things are all kind of linked together, not necessarily kind of perfect representations of everything, the exact shape of the molecule. You're just kind of saying this is how everything is connected together in the same way that a Lewis structure isn't necessarily showing 3-dimensional shape, just how atoms are connected. If we look down below, we have more complicated condensed structures with branching. And so when we look at these, we can when we're parsing out what a structural formula looks like, it's going to be really helpful just to try to find the longest chain of carbon atoms. And so we can see basically there's 4 and then in a row, and then the 5th carbon is kind of hanging off the side. So in our molecule on the right, same thing, it's just 5 across. There are 5 carbon atoms across. And so then the differences between these two molecules are in the branches. We can see that in both cases, there's another carbon atom hanging off of the 4th position, but then there's one in the left, there's a carbon atom hanging off the 2 position, and there's a carbon atom hanging off the 3 position. Those are not the same thing. That's what makes these molecules isomers. It is the same number and types of atoms, 7 carbons and 16 hydrogens, see over here. The difference is how they are arranged. When we step up to more complicated structures, like say cycles, where the atoms are say in a loop, you run into issues that condensed structures really just don't work too well. You're basically just drawing out the entire molecule as it is and writing in all of the carbons. You can note we kind of get away with just kind of dumping the H2s next to the carbon like we've seen in condensed formulas, but a lot of times you just end up drawing a Lewis structure, right? The pyridine here. There's not really a good way to condense this and write it in a succinct way that really avoids anything. You're just drawing out the whole Lewis structure. So we need to come up with a different way to describe these molecules. And that's where line angle formulas come in. So line angle formulas are a representation of organic molecules where we're going to use lines and vertices, angles, vertices, to represent bonds and carbon atoms. So cyclohexane, this would be chlorocyclohexane, sorry, this would be the condensed formula. All the carbons, hydrogens, and chlorines are written there. And the line angle formula is right here. So you'll notice all of the C's and H's are missing. So when you have a corner like this, it is implied that there is a carbon atom at that corner. So there's a carbon atom at every single basically join angle of lines. Because organic molecules are composed of carbon, there's a ton of carbon in there. If we avoid writing out all of the C's, we're going to get a lot of bang for our buck, right? Just time-wise, it's going to be a lot easier. We know that the reader can always assume or interpret that everywhere you see an angle, there's a carbon atom. You'll also note that there are no hydrogen atoms written. We know here in the pyridine molecule that there is a hydrogen atom attached onto each of the carbon atoms, but basically there's nothing attached on here. That is because we don't write the hydrogen atoms. It is implied that you would need as many hydrogen atoms or lone pairs to complete the octets of each of your atoms. So you don't need to write any sort of explicit representation of those hydrogen atoms and of those lone pairs to see where it would be, because the reader, whoever's looking at the molecule, can basically figure out what needs to be there for everything to have an octet. We're going to follow those rules. Nitrogen, always has 3 bonds and a lone pair. Well, this nitrogen atom has 1, 2, 3 bonds, so there must be a lone pair on it. Chlorine, as a halogen, tends to have 1 bond and then 1, 2, 3 lone pairs. So you as a chemist can know that, and if everyone knows that, we don't need to all write them out. So let's look at some examples. Let's draw the line angle formula for the following molecules. We've seen these before. This is ethanol, this is propene, and this is dimethyl ether.
So we want line angle formula for the following molecules. So line angle formula means we're just going to be drawing lines to convey the bonds between carbon atoms. So when we're doing this, we really want to focus on what are my non-hydrogen atoms in a molecule, because that's really the only thing you're going to communicate. So we can see we have 1, 2, 3 non-hydrogen atoms. Okay, I have the carbons, the 2 carbons, and the oxygen. And so what I can do is I can start with this carbon atom. That's just basically going to be a dot. I'm going to draw a line because it's bonded to another carbon atom. And then I'm bonded to an oxygen. So I draw another line to the O. And we draw them at these angles so that way you can see basically that at the end here is 1 carbon atom. In the middle here is the 2nd carbon atom at that bend. That's why it's line angle. The angle, that bend we want to show, is where the carbon atom is. And then I do write the oxygen. Okay? So I do write the oxygen, and I write the H that's attached to the oxygen. So I don't need to include any H's that are attached onto carbon atoms, because the idea is you can figure those out, or you can imply those are implied. But I do want to explicitly kind of note any of the hydrogens that are attached onto oxygen, right? And we can figure out the number of hydrogens based on the fact that carbon tends to form 4 bonds. We know at the end of this line, there's a carbon atom. It is currently in this drawing, only 1 bond is depicted. So because I need 4 total, there needs to be 3 other bonds, and we can just imply that they're all to hydrogen. So we all just agree that we don't write any of the hydrogen bonds. And that way, the reader, whoever's looking at this drawing, can figure out basically how many other hydrogens there have to be. In this middle carbon atom, we have 1, 2 bonds that are drawn. So we need 2 more. So 1, 2 hydrogens are implied to be hanging there. All right. And so if we want to come to our second molecule, then we have, in this case, 1, 2, 3 carbon atoms. So we're going to write those 1, 2, 3. So again, we just use those bends. You can see basically because they're all carbon, we don't write anything. We just keep them as lines, 1, 2, 3. What we do need to denote is that there's a double bond here. Because we have those 2 lines between carbon and carbon, between the first and the second carbon, that implies that there is a second bond here. So that means I have a double bond. And we need to include that double bond because we know that each carbon tends to form 4 bonds, and we need to explicitly show that this first carbon atom has 2 bonds right there, right? 1, 2. So that means there would be an H and an H. This middle carbon has 1, 2, 3 bonds already. It's only going to need 1 other hydrogen, which we can see right there, right? It's just the CH that's hanging off on the side. For my bottom molecule, again, I only look at the non-hydrogens. I have 1, 2, 3 of them in this molecule. And so if I'm going to go to draw them, I'm going to draw the same idea, but because this middle atom is an oxygen, I write that out. And then I draw another line to my third carbon, my third atom that is the carbon. So 1, 2, 3. In the case of this, because this middle oxygen isn't bonded to any hydrogens like the top one was, we don't have to write anything. We don't have to write the lone pairs because, again, you know that oxygen tends to form 2 bonds, 1, 2, and have 2 lone pairs. So it's just implied there's going to be 2 lone pairs on that oxygen atom. These carbons on the outside only have 1 bond that's shown. So that means they would need 3 more. 1, 2, 3 hydrogens are hanging off the ends of both of them. So we can have really concise descriptions of really complex Lewis structures and basically kind of clean out the fluff. And one of the things about it is when you're dealing with the organic chemistry, you're focused on those carbon atoms. That's what you care about. And so the hydrogens are just kind of there to fill out the octets to kind of round it out, make the molecule stable. They're not really that interesting in terms of the structure of the molecule. They don't make the molecule any bigger or really anything like that. You really care about the carbons that kind of make up that backbone of the molecule. And oxygens, those non-hydrogen atoms overall.
Let's look at some examples going the other way. We would like to write the molecular formula for each molecule, and I have 3 line angle drawings.
So now we want to go the other way. I have some line angle formulas, and I want to know the molecular formula for each of those. So when we're interpreting these line angles, we want to still be focusing on basically how many non-hydrogen atoms do we have, and then we can kind of fill in the gaps. And basically what we're looking for is every angle. So we'd be tempted, it's very tempting to normally look at this and be like 1, 2. But we don't want to forget on the end here is still a carbon atom. 1, 2, 3, 4. No explicit atoms were written. It's just there's no symbols, right? So that means they have to be carbon atoms, which means we know right away that the formula has to be C4 something. And so there are 4 carbon atoms in this molecule. So the question is, how many other atoms are there, and what are the other atoms, and how many are there? So we can figure this out by basically taking this and kind of taking it into a kind of more traditional Lewis structure, where those are bonds between carbon atoms. And so we want to think, well, how many total bonds should a carbon atom have? And the answer is 4. Okay, so each carbon atom should have 4 total bonds. None of these do as written, so we need to fill the rest of them bonds. And they are always going to be filled with bonds to hydrogen. Each hydrogen forms 1 bond. So this atom currently only has 1 bond, so it needs 1, 2, 3 more. H, H, H. This carbon atom currently has 1, 2 bonds, so it's got 2 single bonds, so it just needs 1, 2 more. This carbon atom also matches the 2. It needs 2 more hydrogens. Carbon atom on the end only has 1, so it needs 1, 2, 3. And so what we can functionally see is basically all the rest of the bonds are filled with hydrogens, or are made up of hydrogens, and then we can just go through and count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be C4, H, 10. And C4H10, a lot of atoms in there. This is a really cluttered depiction. And really the idea is this is a much more simplistic depiction that conveys all the necessary information. One of the real reasons we also do this is just much shorter to draw, right? In terms of time, if you are writing a lot of molecular structures, this is going to be a pain to draw. And it's kind of clunky, right? There's a lot of information here. Those hydrogens really don't matter. What really matters is all the carbons. And then this just doesn't really convey enough. All right, so here on our second one, again, we kind of want to trace out, I do have some symbols. That's a Cl. There's an atom here. There's no symbol, so that has to be a carbon. And then I have another Cl. So we know there is C and there are Cls. And so I know it's at least going to be C I only have one of those. And then Cl2. So I know there's 2 chlorine atoms. Chlorine is a halogen, right? It's that last column before the noble gases on the periodic table. They tend to only form 1 bond. So the rest of this is going to be occupied by lone pairs. So if we kind of draw out our Lewis structure, we'd expect each chlorine to have 3 lone pairs to round out its octet. So those are going to be done. Those are kind of the idea of that decoration hanging out on the outside of the atom. So chlorines are done. Those have octets. The carbon atom does not. So again, we need to fill out. We only have 2 bonds. We need 2 more bonds. They're both going to be to hydrogen. CCl2, H2. All right, so now we got kind of a big one, lots of lines, but we can still interpret it in the same way. 1, 2, 3, 4, 5, 6. So I know there has to be 6 carbon atoms in this molecule. So C6 is going to be the start of the formula. And, you know, we can still always figure it out by just taking this and turning it into sketching out a skeleton. Just explicitly write all those carbon atoms. It's a more complicated shape of a molecule. The structure is more complicated, but we can still understand everything that's there. Go through and just add up to 4 bonds. This carbon atom only has 1, so it needs 1, 2, 3. This carbon atom has 1, 2, 3, 4, so it's done. It's not bonded to any hydrogens because it's bonded to enough carbons. This carbon atom, 1, 2, it needs 1, 2. This carbon atom, 1, 2, it needs 1, 2. This carbon atom, 1, 2, it needs 1, 2. This carbon atom, 1, 2, 3, and then the 4 is right there. And so one of the things we can start to see, so we need to count those up. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6, H12. One of the things we can really start to see is as the molecules get more complicated and more kind of lots of hydrogens filling it in, it's really hard to even this looks even more complicated than it needs to be, but those hydrogens really aren't affecting the overall structure of the molecule, overall kind of pattern or shape of the molecule that we can see right here that is very clearly conveyed with just kind of the line angles. But here it's really kind of clustered. There's a lot of stuff packed in. Those hydrogens are just decoration, kind of rounding out the octets. This really shows what we're looking for, what we're interested in, the carbon atoms.
Another video down, looking for questions on participation 428. There was 1 in this video. That's halfway, that's halfway through, 2 videos into this set. So we already got 1 participation question. Look in the back half of this set of videos, see if we find some more questions. See you there, bye-bye.